So, we discuss Bose-Einstein condensation today. We know from Bose-Einstein statistics the B distribution Ni is 1 by B e to the epsilon I beta epsilon I minus 1, where B is e to the minus beta mu. Okay, and this is for non-degenerate case. When there is degeneracy, we can write Ni is Gi by e to the beta epsilon I minus 1, where Gi is the degeneracy of ith quantum state. Okay. Let us first consider let us now consider the behavior of the constant B that appears in the BE distribution just mentioned above. So, this quantity beta, this quantity corresponds to the partition function of the or in the partition function in the Boltzmann distribution or the chemical potential in the Fermi-Dirac distribution. Now, we need to calculate what is the value of B. So, we will calculate the value of B now. So, we know sum over I Ni gives N. Suppose this is our equation 1, where N is the capital N is the total number of particles. Now, we consider or now we evaluate how does B, the quantity B depend on temperature. Okay, so as we discussed or as we used before, we can consider the density of states spinless particles moving in a box of volume V is, we can represent like G epsilon is V by 4 pi to the 2 times twice m by h cross to the 2 whole to the 3 by 2 times root over epsilon. Suppose this is our equation 2. Now, let us assume that we can replace the summation over discrete energy levels by an integration over a continuum of energy levels. Then the constraint of equation 1 means sum over I n I equals to capital N. Then the constant of equation 1 becomes sum over I n I can be approximated to integral 0 to infinity n epsilon d epsilon, and we represent this equation as equation number 3. So, using Bose-Einstein distribution and the density of states of equation 2, we get or we obtain V by 4 pi to the 2 twice m by h cross to the 2 to the 3 by 2 0 to infinity root over epsilon by b e to the beta epsilon I beta epsilon minus 1 d epsilon equals to n. So, this is our equation number 4. Okay, suppose this is our equation number 4. Now, we consider y is beta epsilon. So, when epsilon goes to 0, y goes to 0, and when epsilon goes to infinity, y goes to infinity. So, the if we substitute y equals to beta epsilon in equation 4, we get V by 4 pi square get v by 4 pi square times twice m by h cross to the 2 whole to the 3 by 2 and then integral 0 to infinity root over y dy by b e to the y minus 1 equals to n. So, suppose this is our equation number 5. Maybe we can write this as equation number 5, y equals to beta epsilon, and this we make equation number 6. Okay. So, we define the function. Now, next what we consider another function. We consider a function, f which is function of beta b is root 2 by root over pi 0 to infinity root over y dy by b e to the power e to the y minus 1. So, this is our equation 7. Now, if we substitute f v in equation 6, we get, so from or by substituting f b of equation 7 into equation 6, we get v So, if we substitute the value of f v of equation 7 into equation 6, we get v m k b t by twice pi h cross to the 2 3 by 2 times f v equals to n. And suppose this is our equation number 8. Okay. Next, what we do? We plot, if we plot f b versus b, the plot of the b versus b looks like, the plot of b versus b looks like so it looks like this. I will explain this one in a while. For large b, for large value of b, we can see f v is nothing but 1 by b. This is because for B much larger than 1, we can write so for when B is very large, you can write 2 by root over pi times integral 0 to infinity root over y dy by B e to the y minus 1 can be approximated as 2 by root over pi 0 to infinity root over y dy B e to the y, because B is very large, so we can neglect minus 1 and this gives 1 by B. Okay, so thus from equation 8 we can write for large B value. So, for large B value we can write B is V by N, then M K B T by twice pi h cross to the 2 whole to the 3 by 2. And suppose this is our equation number 10. Okay. But we find that the integral cannot be evaluated below B equals to 1 or when B is less than 1. Okay, so this equation 8 cannot be evaluated when the value of B is less than 1. This is because there is a singularity at B equals to 1. Okay. This is important to note. That the value of B cannot be less than 1 and there is a singularity at B equals to 1. Thus, the Bose-Einstein distribution is Ni equals to Gi e B e to the epsilon I by kBt minus 1. So, if B is less than 1, there is a possibility of an energy level epsilon 1 such that Ni is negative. Okay. Clearly, we cannot have a negative occupation number or number of particles, negative number of particles or occupation number in any energy level. So, we expect beta has to be greater than or equals to 1. Beta, not beta, B has to be equals to greater than or equals to 1. And for this reason, in the above plot, B starts from 1. Next, we see what is the maximum value of Fb when B equals to 1. So, next we see that Fb takes a maximum value at B equals to 1. The maximum value of B is when B equals to 1 means F1 is 2 by root over pi 0 to infinity where zeta x is the Riemann zeta function. Defined by so we get the maximum value of Fb means at B equals to 1. So, when B equals to 1, we get the value of F is 2.612. Suppose this is our equation number 11, and F1 is nothing but zeta 3 by 2, where zeta x is the Riemann zeta function defined by zeta x equals to n goes from 1 to infinity n to the x, 1 by n to the x. So, this is our equation number 12. Next, what we do that we obtain the fact that if B has a maximum value of is somewhat disturbing. Okay, so if B takes the value 2.612, which is somewhat disturbing, which we will explain in a while, because n is constant and from equation 8 we have this suggests, the equation number 8 suggests, so this suggests that as the temperature goes down, or as the temperature decreases, FB should increase. But if FB has a finite maximum, then below some temperature TB, which we define as Bose temperature, the number of particles we find by integrating the Bose-Einstein distribution over all energies is less than n, the number of particles in the system. Thus, we can write so what I mentioned is, since if B has a finite maximum, then below some temperature TB, the number of particles we find by integrating Bose-Einstein distribution over all energies is less than n. That is the number of particles in the system. So, in that condition, means when T is less than TB, and for all B values, we can write V by 4 pi square by times twice pi m k by T by h cross to the 2 whole to the 3 by 2, and then integral 0 to infinity root over y dy by b e to the y minus 1 is less than 0. Okay. So, the situation becomes clear if we plot the population density in epsilon as a function of energy. function of energy epsilon for several temperatures, for different temperatures. And the plot looks like so this is the case when T is 1.1 times TB, and for this case T is 1.5 times TB, and this is the case for T equals to 0.3 TB. So, we considered three different temperatures, temperature regions. One is much larger than TB, one is much lower than TB, and one is very close to TB. Okay. So, what we get from this plot? Okay. So, for T is greater than TB, when the temperature is larger than or greater than TB value, we see a smooth distribution curve that for high temperatures approaches the distribution expected for a Maxwell Boltzmann gas. The area under the curves for T greater than TB are independent of temperature. Now, we are more interested into when T is less than TB. Okay. So, for or when T is lower than TB, strictly speaking, we cannot evaluate the population density since we do not have a solution for the parameter B. At the best, we can do is we set B equals to 1 for T less than TB, and we find a distribution that is sharply peaked at low energy, but the peak is not high enough for the area under the curve to give the correct result for the number of particles in the system. So, when T less than Tb, strictly speaking, we cannot evaluate the population density, since we do not have a solution for the parameter B. At the best, what we can do, we set B equals to 1 for T less than Tb, and then we find a distribution that is sharply peaked at low energy that we have seen in the above plot, but the peak is not high enough for the area under the curve to give the correct result for the number of particles in the system. So, in the above expression and the above plot, we can just replace this beta epsilon by Kb times Tb, right, because we cannot really evaluate for T less than Tb. So, what we get that the temperature Tb, the temperature Tb is important because at this temperature the particles start to disappear. Okay, so V mkb, now we substitute T by Tb by twice pi h cross to the 2 to the 3 by 2 zeta 3 by 2 gives us n. So, this is our equation number 13. Thus, Tb, we can, from this above expression we can calculate Tb. Thus, the value of Tb is twice pi h cross to the 2 by mk n by zeta 3 by 2 times V to the 2 by 3, and this is our equation number 14. Now, the question is, where are the missing particles for T less than Tb? Okay, the answer is in the ground state. How? We will explain. Okay. The problem which we now need to rectify is that when we replaced the summation over discrete energy levels by an integral over a continuum of energies in equation 3 like we omitted when we did the integration, when we replaced the summation by integration, we integrated over 0 to infinity, and by doing so, we basically omitted the particles in the ground state. Okay. Since the lower limit of the integration is or integral is 0, we should assume for consistency that the ground state has 0 energy, but the distribution function G epsilon is proportional to root over epsilon. So, at 0 energy, the density of states is 0 and the population in the small energy range zero and d epsilon is 0. So, it says it means that the integral in equation 3 only calculates or only estimates particles in the excited states, omitting or ignoring those in the ground state. Remember, we did similar exercise in FD distribution, but in FD distribution in the ground state at the max we can have two particles or when there is no spin of the particle, only one particle can be present in the ground state for FD statistics. So, it considering the value of n, number of particles is very, very large. So, that one does not, if we neglect that one term, or at the max we can have two particles in the ground state when particles will have a plus up or minus up spin. Okay. So, for FD statistics basically we can safely ignore the number of particles in the ground state, because the total number of particles n is much greater than 1. Whereas, in case of BE statistics, since there is no restriction in the number of particles in the ground state, we cannot neglect or we cannot ignore the number of particles in the ground state. So, we made, as I mentioned, we made the same mistake when we consider the Fermi gas. But in that case, there could be only two particles in the ground state. Assuming degeneracy 2 for spin half particles. In other words, we omitted two particles out of a large number of particles n. And this did not affect our conclusions. But for a Bose gas or gas molecules which are obeying Bose-Einstein statistics, for a Bose gas there is no limit in the number of particles that can be present in the ground state. So, if we omit or if we ignore the ground state, from the integration we can make or large error. Large error for B distribution. Thank you.